Welcome back, physics fans. Here we are in lesson 1 of the work, power, energy chapter. It's the same beginnings for both physics and 11, so let's just go through this. Another way of describing and understanding nature is in terms of energy. The use of energy concepts to describe nature is helpful, but is not a new or independent way of analyzing the universe. Energy considerations are simply Newton's laws expressed in different terms, just as hola has the same fundamental meaning as hello, 안녕하세요, Nihoma, buenos dias. Lots of ways to express it. In physics, we looked at momentum, which is just Newton's third law, and Newton's second law put together in a new way. It was just, we came up with good information for collisions and stuff like that. And now here's a new one. Remember how society messed up the terms mass and weight? How much do you weigh? Well, physics uses the term work, and it is different than how society uses it. In physics, work, capital W, is done when a force, F, is exerted on an object and is displaced, V. The amount of work is the product of the force and the displacement. Force times displacement times the cosine of the angle. Force, boom, d, distance, boom, and theta is the angle between the force and that. In Physics 11, we generally don't even deal with the cosine of the angle because we're not doing stuff in 2 dimensions and stuff like that. We just do it in 1 dimension. And work is measured in joules, and that's the same unit as energy. Okay, so force and distance displacements are vector quantities, and therefore the direction is important. And in Physics 11, we want them to be in the same direction, so that we don't have to worry about that. Because if they're in the same direction, if the force is this way and the displacement's that way, the angle between them is 0 and the cosine of 0 is 1. So that just disappears. But interesting that their product, vector times vector, is actually a scalar. For instance, suppose you push a very heavy crate across a frictionless floor. You exert a force on the horizontal direction which moves the crate in a horizontal direction. Boom, it moves to the horizontal. If you exerted a force of 250 newtons and moved the crate 4 meters, the work you did on the crate would be force times distance, force 250 times the distance in the same direction, 1,000 joules. The cosine is left out because it is in the same direction. Okay, now consider a child pulling a wagon as shown. The child exerts a force at an angle, Fx, boom, up at an angle, and the component of the force is in the direction of motion. Only a component of it, not all of it. And the force component in the y direction produces no displacement. So how much he lifts it is not actually moving it to the right. And therefore the upward component does not do any work. Because a force this way and, a displacement that way and a force this way, the angle between them, let's do it here, the angle between them is 90 degrees and the cosine of 90 equals 0. So that formula up there, this becomes 0, so the work becomes 0. Okay, so let's just take a look at it. If the child exerts a force of 25 newtons on the wagon at 30 degrees and the wagon moves 4 meters, then we just go force times distance times the cosine of 30, which is 87 newtons. Okay, lastly, there are 2 considerations when there are no work. First, when the person exerts a great force on the wall, although the force is great, there is no movement. The wall doesn't move. No work is done. This is where it seems awfully strange. This guy is going to be sweating for hours, and he's pushing really hard, and is poodling out, and it seems like he's using a lot of energy, a lot of joules of energy. Nope, no work is done. That's why it's against. So homework is really no work. You're not doing any work. Physics work, that is. Second, a heavy suitcase is carried a distance horizontally. But wait, you say the force is acting to hold up the suitcase over a distance. Surely there must be work done. If this evil thought were running through your mind, reread the definition of work. It is very important that you understand this information. You're lifting it up. Yeah, maybe it took a tiny bit of force to start it moving, but overall, you could walk 100 meters and you're not pushing it this way at all. You're just lifting it. No work is done. Heavy backpack and you're walking down the road, you're not doing any work. Okay, let's do some calculations here. A 10-kilogram block is lifted a height of 4 meters at a constant velocity. So just so you understand the free body diagram, he's lifting it. And there's a free body diagram, there's a force of gravity down. And since it's at a constant velocity, the net force is 0. So this has to equal that. So the weight of that force of gravity is mg, which is 10 times 9.8. And lifting it up, and it goes a height of 4. So the distance up is 4. So work is equal to the force times the distance. The force that you're lifting it up with is 98 newtons. And the distance that you're lifting it is 4 meters. So 4 times 98 is 392, and the unit would be joules. A J would be a good one to abbreviate that with. How much work is done by that person lifting the block? The lift force times the distance, boom. A block is pushed up the frictionless slope from the bottom to the top at a constant speed. So, how much work is done? F push is 28 newtons. 28, oops, mistake. 30. And the horizontal distance is 12, and the vertical distance is 5. Okay, so we don't use either of these distances. We use, because the force is in this direction, it'd be nice to have the distance in that direction. If they're in the same direction, then we don't have to worry about the angle. So 5 squared plus 12 squared, all square root, it just happens to be exactly 13. So this is a 13-meter diagonal line. So work is equal to force times distance, which is going to be the force of 30 newtons times a distance of 13 meters. And that is 390 joules. Now here we go. The same block is lifted from the bottom to the top at a constant speed, from here all the way up. And I'm telling you now to move it from here to here. Okay, lift it up, carry it, and pop it down. You would have done no work because the force is up, but you're moving this way. And then you get here and then lift it up. That's where you do the work. So instead of taking it up the ramp, you take it over to here and then lift it up. Well, taking it over there was no work, and the work to lift it up is the same. To get that block up to here is the same, no matter which way it is. That's why I'm just telling you the truth now. The work is the same as in example 3. So we know the work is 390. Find the force on the block to lift it. Okay, the push force was 390 beforehand. How much is the force now? Well, we're told that if you're going to lift it, the force of the lift times the 5 meters up is going to also equal 390 joules. So the lift force is going to equal 390 joules divided by the 5 meters. Okay, and I believe that's 78 newtons. So what is the weight of the block? The weight of the block is 78 newtons because your lift force is the same as the force. That's pretty interesting. Okay, the lift, not the mass, yeah, just divided by 9.8. I know it's confusing, but we'll get going on this. It'll be easy, much easier now. Okay, number 5. A 3,000 kilogram truck traveling at 72 kilometers an hour. Just telling you, divide that by 3.6, you get 20 meters per second. Because we don't like these units when we're starting to work with work power energy. Because just we don't. Hits the brakes and comes to a stop in 40 meters. Comes to a stop, and the distance is 40 meters. What amount of work was done to stop it? Well, the work is force times distance. We need the force that's stopping it. So this is how I'm going to do it. I have 3 of the kinematic properties. We have VI is 20, VF is 0, the D is 40 meters. So we're going to calculate the acceleration. So we get VF squared is equal to VI squared plus 2AD. 0 is equal to 20 squared plus 2 times A times 40. So this is going to be negative 400. How did I get the negative? This goes over once it's squared. 400, put it over there, negative 400 is equal to 80 A. And now A is going to equal negative 400 divided by 80. A is equal to negative 5 meters per second. It's decelerating. We expected it. Now, F net is equal to MA, and the mass is 3,000 kg, and the acceleration is negative 5 meters per second squared. So the net force is going to be negative 150,000 joules. And that net force is that frictional force. We sum up all the forces, and it's just going to be the frictional force. So this is going to be the frictional force. So that's the force that's stopping it. So work is going to equal negative 150,000, sorry. No, newtons. Oh, bam. Caught my answer, but error, but you probably did before I did. Let's put it in black because Mr. Curl messed up. And then we're going to multiply it by the distance 40. And we get negative, and now I have to multiply that out, and that'll be about 6,600,000. 6 million joules. Okay, just gonna pull up the calculator there to verify that. So we got 150,000 times 40 is 6 million. Good. Okay, now it's a negative. Why is it a negative? Well, it's because your distance is this way, but the force of friction that was slowing it down was this way. Does that make sense? Well, sure, we could have just said this force, period, no matter what, and then that distance, boom, and the angle between that is 180 degrees, and the cosine of 180 is negative 1. That would have given us the negative. So we could do the logic in physics 11, or in physics 12, go ahead and do the cosine. Negative 6 million joules made it come to a stop. That's how much work was necessary to stop it. Okay, so there's some extra questions here to do here, and the answers are to the right. Try them out. I'll be back here with some answers. Oh, the answers are there. Hope you paused it. Maybe you didn't. Here we go. A force of 20 newtons is pushing a box along the floor for a distance of 8 meters. How much work was done? Force is 20 newtons, distance 8 meters, 160 joules. What happens if there was friction? No difference. As long as the force was 20 and the distance was 8, maybe there was a 20 newton push force, frictional force back, so there was no acceleration. How much work was done? 160. What happens if there was no frictional force? Well, as long as you maintained a 20 newton force over that 8 meters, 160 joules was done. Yes, it was acceleration. Same amount of work, 160. Number 2, a 0.1 kilogram puck is accelerated at 5 meters per second squared for half a meter across a frictionless air hockey table. How much work was done on the puck? The work is force times distance. The force is mass times acceleration. We have the mass, we have the acceleration, 0.1 times 5, and that is going to be 0.5 newtons is the net force. 0.5 times 0.5 is the distance, 0.25 joules of work was done. A bulldozer pushed a large rock with a force of 5,000 newtons at a constant speed for 20 seconds. How much work was done? Well, 2 meters per second for 20 seconds, the distance would have been 40 meters. The push force is 5,000, so then that is just going to be 200,000. Okay, work is equal to force times distance. How much work is required to lift a 50 kilogram object straight up at 10 meters per second? Now, that's a tricky one because is it at a constant rate, right? We have to kind of know, because if it's not at a constant rate, he could be doing a lot more work because he's lifting more than the 490 newtons that this is. So we'll have to do an assumption that it's at a constant rate. And so this object is being lifted up. And we're going to assume that it's at the constant rate. So these have to equal the same. This is just mg, and this is going to be 9.8 times 50, which is 490 newtons, and the distance times 10, so we get 4,900 joules. Work is equal to force times distance, and the force is 490. That's a 490, and the distance is 10. Sorry, being sloppy. Okay, here we go. Some concept ones. Here we go. How much work is being done holding onto a 5 kilogram block and moving 2 meters to the east? It's going to be 0. Okay, because you're holding onto it, so you're lifting up on it, but you're moving this way. That's 0 joules. And a 5 kilogram block is sitting on a 2 meter shelf above the ground. How much work is being done? It's sitting there. There's no motion. Yes, there was work probably to move it up there, but there was no motion being done. So again, that is 0 joules. OJ. And number 7, here's the big learn here. No answers here. You got to understand it. And I'm giving the mass, 196 Newton mass, is being dragged along a level floor with 50 Newton pull force, while a 40 Newton frictional force is being applied. So let's draw the free body diagram. There's a normal force, there's a force of gravity, and that is 196 newtons. There's a pull force. Yeah, it's not a free body diagram. I've already put numbers in it. I ruined it. No numbers. Okay, so this is just our force diagram, not a free body diagram. Force of friction equals 40. This is going to also equal 196. And there's a net force. Let's just draw the net force here in black. Gotta have the sound effects. Net force is 10. So we have all the forces. Okay, the object is accelerated at 80 and travels 87 meters in 12 seconds. Okay, interesting. Fine. How much work did the pull force do? So every one of these forces, big idea, every one of these forces, including the net force, we can calculate the work done. So how much force did the pull force do? 50 times 84. How much work did the frictional force do? 40 times 84, but it'll be negative. What is the net work done on this mass? That'll be 10 times 84. Because net work done by the net mass. What is the mass of the object? Well, you can calculate the acceleration. Right? And then you can get the mass by Newton's second law. And what is the coefficient of friction? Well, the coefficient of friction is just mu times mg, or the normal force here. And so mu is going to be 40 over 196. That's pretty cool. So how much work did the normal force do? 0, because it moved this way and the normal was up. And how much work did the force of gravity do? In this case, nothing, because it was going down. When can the normal force do work? Well, if it's on a surface and you're moving along the surface, the normal force never does any work, because the normal is up to the surface. So when does the normal do work? When your motion is also that direction. So in an elevator, the floor does a normal force on you, and it does work because it's pushing you up. There we go. Sorry, long video. Hope you enjoyed it. Here comes the next one. Let's listen to the jingle. Remember, subscribe, like, comment,